We can make it to a triangle. I could tell. Pull up.
This video will discuss MGSE7 G3. Describe the two-dimensional figures, cross-sections, that result from slicing three-dimensional figures, as in plane sections of right rectangular prisms, right rectangular pyramids, cones, cylinders, and spheres. Although students have not formally been introduced to cross-sections, they have seen them within science and social studies texts, often referred to as cutaway views. Many students have cut foods which produce cross-sections. In 7th grade, students slice three-dimensional shapes such as right rectangular prisms and pyramids, cones, cylinders, and spheres to reveal two-dimensional shapes referred to as cross-sections. In high school, students identify two-dimensional cross-sections of three-dimensional objects and extend their thinking to identify three-dimensional objects created by rotations of two-dimensional objects. In the concrete stage of instruction, within the concrete representational abstract phases of instruction, each mathematical concept is modeled with concrete materials such as red and yellow chips, cubes, base 10 blocks, pattern blocks, fraction bars, and geometric figures.
The goal of the concrete stage of this standard is for students to become familiar with the idea of slicing figures and making predictions about what the resulting cross-sections will look like. These students have created three-dimensional shapes with Play-Doh and are using dental floss to slice the shapes vertically, horizontally, and diagonally. They begin to make generalizations about the direction of the cut and the relationship between the cross-sections and the base. Listen as the students make a prediction of what two-dimensional shape will be revealed with their vertical slice.
Come on. We can make it to a triangle. I could tell. Pull up.
Oh, you can't mold it after the fact. It's created by the slice. So what 2D shape was created when you sliced it with the floss?
A circle.
A circle.
Semicircle.
Okay. What shape is this?
A sphere.
That's the flat shape.
Oh, circle.
Circle, that's your cross section, that's the flat shape. So you were only able to create a circle. Try to cut it one more time and see. As students work with concrete materials, it is important to explicitly address the misconceptions that may arise. Students may view the chunk of the three-dimensional figure as the cross section. As seen in the previous video, the teacher should reinforce the cross section is the two-dimensional figure created by the cut. Do your slices. So you've already did triangle. How did you know a triangle would be able to be created?
I just cut it.
Because it's a triangle prism. Okay. What if you sliced it parallel to the base?
Like this?
Yeah,
That would make a rectangle.
it would make a rectangle. Do you think you'd be able to make a circle out like that?
Probably not.
Probably not. Why not?
Because on the circle has no.
Oh, yeah, good. Nice job, gentlemen. Did you notice how the students were able to visualize the cross sections without slicing the shapes? This shows the progression to the representational phase of the CRA model.
In the representational stage of the concrete representational abstract instructional model, concrete models transform into a representational or semi-concrete level, which may involve drawing pictures, using circles, dots, and tallies, or using stamps to imprint pictures for counting.
As students progress through this standard, they should view images such as this one and identify and describe the resulting cross-section. Some students may find it useful to recreate the three-dimensional figure themselves and draw the plane which creates the cross-section. In the task, What's My Solid from Grade 7, Unit 4, Georgia Department of Education Mathematics Frameworks, students visualize described cross-sections and use their visualizations and logical reasoning to determine which three-dimensional figure or figures the cross-section relates.
Listen as these students discuss, using their visual model and their logical reasoning, why a cube could have parallel cross sections that are congruent rectangles.
Because when you cut it in half, it makes an equal rectangle.
And it says that all of the rectangles are congruent, and when we looked at congruent, same size and same shape, that's what a cube is.
Okay, is there another figure that it could be?
I don't know. I
Besides a cube?
can't see it.
Well, think about the three-dimensional figures. Is there another three-dimensional figure?
I
You
know
cut
it
it
can't
parallel
be
to
a
the base.
rectangular.
Oh, parallel to the base? Rectangular to the base.
Rectangular prism.
Vocabulary is an important component when discussing cross sections. While discussing scale figures in the ratio and proportions unit, students were introduced to the concept of shapes that are similar. Here within the task, What's My Solid? From the Unit 4 Mathematics Frameworks, students apply the idea of similar shapes to the extension within the task. A set of my parallel cross sections are circles that are similar but not congruent. Listen as this student grapples with this clue.
So now when you're looking at C, a set of parallel cross sections are circles, so they're both what kind of shape? Circles, and they are similar but not congruent. So what would be different about them? One is smaller. Okay, so what three-dimensional shape would produce that? You can look at the list of three-dimensional shapes. We have prisms, pyramids, cones, cubes, and cylinders. And why would you think that it's a cone?
Because if you were to cut a cone, then if you were to cut a cone, it would get, I don't know.
Why don't you try to draw a picture of a cone, and maybe that'll help you.
See, isn't a cone a circle but smaller upward?
As you go up, yep,
Yeah,
that's what you were thinking.
yeah, if you like cut it, like if you were to like cut it, it will get smaller.
So which side, if this is the beginning of your cone, which part would make the smaller circle?
Down here.
Down there. Okay, good.
Students should have opportunities to discuss and compare three-dimensional figures that will produce the same or similar cross sections. Listen as these students discuss which two three-dimensional shapes will produce circular cross sections.
Why wouldn't it be a sphere?
Because it's just like the cone, how it goes smaller upwards.
So what's a sphere?
It's like a 3D circle.
Okay, so it's like a ball, right?
Yeah.
And if you were to slice it, what would the cross section look like? Would they be the same size? So would that work for that one? You said that it would be a what?
Cylinder.
Cylinder. You said that it would be a circle. I mean a sphere. Would both of those work?
Yes.
Okay. Cube Ninja from Illustrative Mathematics can be used during any point of the CRA, concrete, representational, abstract phases. Using Play-Doh, students can physically create the cubes while attempting each question. Students can draw the cube and the planes which would create the cross-section. And students can also use their visualization and logical reasoning to identify and describe the cross-section.
With this task, students engage in multiple standards for mathematical practice. The flow of instruction will determine which of the SMPs is emphasized. As students work with concrete materials, technology, or draw visual representations, they will emphasize SMP 6, use appropriate tools strategically. As students explain the slices that they've used to create their cross sections, they must attend to precision using accurate mathematical language. Allowing students to focus just on the visual representations provided by the task causes them to reason abstractly and quantitatively as they begin to discuss which cross sections could be created by the different slices.